Hello everyone. I hope everyone is safe and healthy. So this video is in continuation with the blog post which you must have read already. It's on magnetic field and magnetic forces. This is in continuation to the last blog post which we did on electric field and electric forces. So definitely there will be a similarity uh, between these two topics. So let's start our discussion. So what thing comes first in our mind when we read this term magnetic is definitely magnets. So whenever we talk about magnets, definitely we have a north and south pole in any magnet because it's not possible to have just one pole in any magnet. It doesn't matter if even if you will cut in half from this side, then that will result in two independent magnets and each having its own north and south pole. Uh, if we talk about the magnetic fields, then the fields always emerge from the north and they terminate on the south pole. So if you want to draw the magnetic fields in magnetic fields on a magnet, so that's how it looks like. Uh, Here we'll show some of the fields going in this way, going in this way, and we have to make an arrow. So this arrow means that the fields are originating from the north, and this closing arrow means that the fields are terminating at the south pole. Um, Whenever we talk about any magnetic field, definitely there should be a customary representation of the magnetic field, just like we denote E with a small arrow which denotes vector. So we denote this as the electromagnetic, or let's say the electromagnetic fields. Better to write it as electrostatic fields. Likewise, the magnetic fields are denoted with a B with a small arrow on it. So that's how we represent magnetic fields. What is the unit of a magnetic field? So if we talk about the SI units, magnetic field is represented with the unit of Tesla, which is the most popular unit, denoted by a capital T. Another unit of that will be Weber per meter square. If we talk about the CGS unit, then the unit is Gauss. And there is a relation between Tesla and Gauss, which is 1 Tesla is 10 raised to the power 4 Gauss. So this conversion will be helpful in some of the numericals in case the units are given in CGS. Um, then we also read in the blog post that any magnetic field is not only produced by a magnet, but it is also produced by any charge which is in motion. And if we see that, let's say this is a wire which is carrying current, and we know that current is nothing but when the electrons move or the charges move. So definitely in this moving charges which result in the formation of a current, that will generate a magnetic field as well. So this particular formula was given by Biot-Savart, and that's why it's called Biot-Savart law, which states that the magnetic field due to any elemental current carrying wire. Why am I saying elemental is? I'm saying if the total length is considered to be L, then I'm saying an elemental length DL, right? So this is a very small piece of length the length of which is considered the DL, and we are interested to find the magnetic field at a position vector R from this DL, which is at P. The reason why we are taking DL as a very small, extremely small length is we can consider that all the points on this length is actually at the same distance R from P, because this is infinitesimally small. So that's the reason why we take a very small element. So Biot-Savart gave a relationship between the magnetic field which is produced due to this elemental length wire, and that is given by dB. Why we are saying dB? Because it's similar to dx over dt. So d denotes a very small quantity. Definitely because of dl, the magnetic field which is generated would be dB. So dB is denoted by mu naught I dl cross r, When I say cross r, it means that it is a cross product because these two are vectors over 4 pi r cube. This is the formula which Biot-Savart gave, and this helps us in turn to find the magnetic fields due to other figures as well. But this is the basic formula. Mu naught is called the permeability of vacuum. So it's permeability of vacuum. If we remember, when we were talking about electrostats, there was something called epsilon naught, and epsilon naught was called permittivity of vacuum. Just like that, mu naught here is called permeability of vacuum, and the value of mu naught is 4 pi times 10 raised to the power minus 7. In other words, we can also write that mu naught over 4 pi is 10 raised to the power minus 7. Why are we writing like this is because if we notice, there is mu naught over 4 pi in the formula, which can right away be replaced by 10 raised to the power minus 7 while solving for numerical questions. So that's how this Biot-Savart law is given, and using this Biot-Savart law, we are going to find the magnetic field. Before moving to that, definitely, since this is a magnetic field, so it has to be there has to be a direction, and the direction is given by right hand palm rule. So right hand palm rule says that you take your right hand, you stretch it, and in such a way that your uh, uh, thumb is pointing towards the current, or let's say the elemental wire, and your fingers are pointing towards the direction vector r. So in this case, if we are going to place a right hand over here, then our thumb will come over here, and definitely our fingers are going to come here. So the push, which will be the push as in the direction of the palm, so the palm is definitely into the paper, so that will give the direction of the magnetic field. So in this particular case, it is going inside the paper, and anything which is inside the paper is denoted by a small cross. That's how the magnetic field is denoted, which is inside the paper. And if it is coming outside the paper, it is denoted by a dot. So this means inside the paper or the plane, and this means outside the paper or the plane. So that is again a customary notation which we'll see in almost all the questions, that anything which is inside is a cross, anything which is outside is a dot, and that's how the right hand palm rule works. So if you are going to do a couple of examples just to understand that how to find the direction, then example 1 says that there is a wire which is in the north-south alignment, and we are saying that its current is going towards north. All right. So if the current is going towards north, we are supposed to find the magnetic field at part A at east, in the east direction. Let's first try to visualize how this looks. So this is the wire. This is a straight wire. Definitely this is north and this is south, and the current is going towards the north side. So north is top. East lies over here. So if you're going to place our hand, if we stretch our hand and we are going to place our thumb over here, and the fingers will point over here, and the push is definitely coming into the paper. So into the paper means the direction of the magnetic field will be like this. So it's into the paper, which is denoted by a cross. If we talk about part B, we need to find the magnetic field at, let's say, vertically up. Any point which is vertically up. Vertically up means it is above the paper. So again, this is north, this is south, current is going towards north. If you are going to place our hand, definitely our hand, although the thumb will lie in this direction, but our fingers will come vertically up. If they come vertically up, a push will come in this direction, which is east. So definitely the magnetic field will now come in east direction. And let's take another part. which is C, and we need to find the magnetic field in the west direction. So in this case, we have this is north, this is south, and this is any point in the west. And if we are going to place our hand, the thumb is going to come here, and the fingers will definitely come in this direction. So our palm will be coming in vertically upward direction, or above the paper, outside the paper, which is denoted by a dot. So we'll say that if this is the point P, then the magnetic field is represented by a dot is coming out of the paper. Let's take another example to understand the directions better, because it's really important to correctly figure out what is the direction of the magnetic field. So this point actually represents a wire, and this wire is into the plane. So it's basically coming into the plane and going outside the plane. So it's vertically down to up. And why I'm showing dot is because the current is coming up, right? So in part A, we need to find the direction of the magnetic field in the east, which is over here. So if you're gonna place our hand, the thumb will definitely gonna come above the plane while we point our fingers over to the east. So push will come over here, and this is nothing but north. So the field will come in the north direction, uh, at any point, let's say on the north, if we are going to shift our fingers over to the north, then the push will come over to the left, and left is nothing but west. So that's where our magnetic field will be pointing. So that's how we figure out the direction of the magnetic field using the right hand palm rule. Let's take this concept ahead and try to find the magnetic field due to a current carrying loop at center. So the loop is definitely a circle, and this is a perfect circle, and this is the center, and the radius is given as r. We are using the Sebert law here, so let's take this elemental strip over here, and this is dl. So what is the direction between the dl and r? It's 90 definitely, because the dl because there's a property of the circle that the radius and a tangent, because this dl just acts like a tangent, it's always perpendicular. So if you're going to apply a formula, then dB will be equal to mu naught, and this loop definitely has a current which is going in the anti-clockwise direction, and the value is I. So using the Biot-Savart law, the dB would be mu naught I dl cross r over 4 pi r cube. Let's try to simplify this. We know that to remove the cross product, we multiply both. So dl times r with the sine of the angle between them. And we just discussed that the angle between them is 90. So we are going to replace this by sine 90 over 4 pi r cube. And this is the magnetic field due to a current carrying elemental wire. But we are interested in the complete loop. So what shall we do? We have to integrate, and we have to integrate for the complete length. So we'll say that the total magnetic field would be the integration. And what are the limits? Limits would be from 0 to the total length of the wire. And the length of the wire is nothing but the circumference, and the circumference of the circle is given by 2 pi r. So we'll place our upper limit as 2 pi r. We have mu naught I. One of the r will get cancelled, and sine 90 is replaced by 1. So that's how it looks like. Mu naught I and 4 pi r square are all constants. Let's take it out. We just have to integrate dl within the limits of 0 to 2 pi r. The integration is very easy. Integration of dl will just be L. So it's mu naught I over 4 pi r square L within 0 to 2 pi r. So this comes out as mu naught I over 4 pi r square times 2 pi r, which finally comes out as mu naught I over 2r. This is the magnetic field if the loop just has one turn, but what if the loop has n turns? So if it has n turns, the simply we just multiply with n. So the magnetic field for the n turns comes out as mu naught I n over 2r. And what is the direction? We just use the same rule. So as per the right hand palm rule, if we place our thumb over DL, definitely the current is going in this direction. So fingers point towards the radius. So the push is coming vertically upwards. So we'll place a dot over here. So whenever the direction is anti-clockwise, the field comes out of the plane. So that's how we calculate that's how we get the formula for the magnetic field due to a current carrying loop, but that too at the center. All right, let's talk a little bit about the magnetic force now. We read in the blog that whenever a moving charge enters a magnetic field, it experiences a force, and that magnetic force is given by Q times V cross B. Cross product once again between the two vectors, where V is the velocity, B is the magnetic field, and Q is definitely the charge. So one more thing, how to give its direction. So direction is given by a right hand rule, where let's say this is the velocity V and this is the magnetic field B. Uh, so to determine the direction, we take our right hand and we curl our fingers from velocity to magnetic field. So if we curl our fingers in this way, the thumb will definitely point into the plane, which will give the direction of the force. So that's how we give the direction. And one thing we need to take care is if the charge is negative, then the force, the direction of the force will be exactly opposite to what we get from the right hand rule. So for example, if we want to if we want to find the direction in this particular case where velocity is over here, B is over here, but here we have an electron. So although we curl our fingers from velocity to magnetic field and we get the direction vertically up, but we realize that electron has a negative charge, so definitely the field will be in the opposite direction. So it is in this direction. Uh, let's take another example. If you want to find the force over here, this is the magnetic field and the velocity is parallel to it in the opposite direction. What is the force? We know that force is Q times V cross B, or it can also be written as QVB sine theta, where theta is the angle between V and B. So in this case, what is the theta? Theta is 180. And what is sine 180? Is 0. If sine 180 is 0, we have the total force as 0 as well. So we understand from this calculation that whenever the velocity is parallel or even anti-parallel to the magnetic field, the force will come out as 0. So there got to be some angle between the velocity and the magnetic field for the force to act on any charge. I also talked about a special case in the blog. So let's discuss about that. So the special case arises when velocity enters perpendicular to magnetic field. What this means is if we write force as QVB sine theta, then if the theta is 90 degree, then the special case comes in where the force is QVB. If the force is QVB, why this is special? Because the trajectory in which the charge moves is something which is worth discussing. So I'm going to explain this by making this magnetic field. So this magnetic field is definitely coming out of the paper, and this is infinite. So it's going infinitely here and infinitely here. And we have a charge, let's say positive charge, which is placed over here and it is pushed in this direction and velocity v. So we are interested in finding what path it follows. So let's try to find out the direction in which the force is acting right now. So applying the right hand rule, if we apply Q times V cross B, then the force in this case will be acting over here, which is exactly perpendicular. Why it's acting exactly perpendicular? Because there is a property of the cross product that the output of the cross product is always perpendicular to the individual values. So the force will definitely be perpendicular to velocity as well as the magnetic field. And the only way it can be perpendicular to both using the right hand rule as well would be acting in this direction. I'll choose a different color here. So it's acting in this particular direction right now. Let's say it moves a little bit and it comes over here. So the velocity is here and the magnetic field is still outside the paper. So where is the force acting? It's acting over here. So we realize that at every point, the force is acting uh, kind of towards a single point, right? So if we tend to make a complete circle, always the force is acting towards the center, and this results in the formation of the conclusion that the whenever a charged particle enters a magnetic field perpendicular, it moves in a circle. So that's why this is a special case, and this is the center of the circle. So we can write that the force which is acting on this charge, it is Q times V cross B, which is nothing but QVB. And since it is moving in a circle, then this force must provide the equivalent centripetal force, which is equal to mv square by r. So if we solve this, one of the v gets cancelled, and the radius of the circle comes out as mv over bq. So this is something worth remembering, that the radius of the circle in which the charged particle moves when it enters perpendicular to a magnetic field is mv over bq. And another important uh, expression which is worth remembering is the time period. So if we talk about the time period, we know that the time period is given by 2 pi r over v. So let's substitute the value of r over here. It's mv over bq. So this v gets cancelled and we are left with 2 pi m over bq. Interesting thing to note about this time period is it is independent of velocity. This is worth noticing. So let's do a quick numerical on this just to help us understand that how to apply all these formulas. So we say that there is a proton and alpha particle are pushed with same velocity in a uniform magnetic field perpendicular to it. Find the ratio of their radius. Interesting question, because although we already know the value of the expression for the radius, it's given by mv over bq. We know that v and b are same for both, but what about m and q? So we need to know one relation, that if we take for the proton, if we take the mass as m and the charge as q, then for the alpha particle, the mass of the alpha particle is 4 times that of the mass of the proton, and the charge is 2 times that of the proton. So keeping these things in mind, uh, we have the radius as, let's say the radius of the proton as mv over bq, and the radius of the alpha particle as 4m v over b times 2q. This comes out as 2m v over bq. We need to find the ratio. So as simple as that, simple algebra, we take the ratio of rp over r alpha, which is mv over bq over 2mv over bq, which comes out as 1 over 2. So this is the required ratio of the radius of the proton and the alpha particle. I hope this video was helpful for you. I hope you understood how to apply the formulas and the concepts. If you still have one of your questions, please post it down in the comment section and I will be happy to address them. So till the next time, please take care.